Up until now, we've only been talking about image classification, where we want to assign a single label to the main content of an image. But what happens if we have multiple objects of interest in one image? For example, let's say we trained a classifier to identify an image as either a cat or a dog. Then I feed this to the model. Is this a picture of a cat or a dog? The model is incapable of handling two objects, so it will focus on the most salient features based on how it's been trained to make a decision. And it will classify this image, which contains both a cat and a dog, as either cat or dog, but not both. Remember the model we trained earlier to identify electronic components? I gave it these two images as test data to see what it would do. Both images contain a resistor and a capacitor. In the first image, it still successfully classified the resistor, but it was not very sure of that choice, even though the resistor was in the position it might expect to find resistors, right in the center of the frame with the leads going out to either side. When I moved the camera down slightly, the resistor was no longer in that spot. In this case, the model focused on the capacitor this time and classified the image as such. Note that it won't always be what's in the center of the image. What the model focuses on has to do with how you train the model. If the resistors were always in the top left of the frame for the training data, then it might focus there when trying to classify something as a resistor. But for this model, it happens to focus on what's near the center, as that's how all the images in the training set were structured. What we've been doing up until now is known as image classification. Image classification is where we train a model to predict the class of an entire image. This works best when there is a single lone subject of one of our classes. When you introduce multiple objects in the image, the classification methods start to break down. Image classification also can't tell you exactly where in the image the object is located, so it's best if all the objects are framed in a similar manner for all the images you're working with. However, we can use other methods to find the location of objects. This is known as object localization. Note that with localization, we don't care about the type of object that's being detected. We just want to know where some kind of object of interest is located. That's where we introduce object detection. With object detection, we want to both locate something in the frame as well as classify it. Object detection can tell us where multiple instances of an object are in an image, as well as discern among several classes of objects. Most object detection methods will attempt to both classify objects in an image and give us an idea of their location and relative size in the frame. They will do this by using what's known as a bounding box. A bounding box is a set of coordinates in the image that could be an x, y, width, and height, or the location of two opposite corners. The idea is that you could use this information to draw an overlay on the original image to get an idea where those objects are located in the frame. Along with the bounding box, you should also get a predicted class and confidence level of that class. For example, a well-trained object detection model might give us a bounding box for the cat with a predicted confidence of 98%, as well as a bounding box for the dog with a predicted confidence of the dog class of 83%. With a little bit of math, you can find the center of these bounding boxes, which should give you an idea where the middle of the object is. This is great if you, say, want to have a self-driving car avoid these objects, or maybe want to have a pan-tilt camera automatically follow them by moving so that the center of the frame lines up with the center of one of the objects. One easy way to do object detection is to do a simple sliding window with inference performed for each window. Let's say I'm trying to determine the location of my dog in this frame. This works best if the window is the same size as your training set resolution. We then feed whatever is under this window to our image classification model, and it performs inference to give us a prediction. Here, it might predict background as the class. Then we slide the window over and send the new set of pixels under the window to the model. Note that I have a little bit of overlap between the two windows. You can adjust the amount of overlap by setting a stride value, usually measured in number of pixels. If your stride is larger than your window width, you won't have any overlap. If it's less, you'll have some overlap. Note that more overlap means a better chance of detecting your object, but it means that you'll need to perform more inferences per still image, which could really slow down your frame rate. We continue this process until the window highlights my dog. Here, the model should predict dog as the class. From here, we could draw a bounding box the size of the window to denote that a dog was detected. However, let's say that we keep sliding the window and marking the locations of dog detections. We might end up with something like this. There were 3 true positives that detected areas of my dog, 1 false positive as the model thought my hanging cables were a dog, and 1 false negative where my dog's back legs were missed. This might be good enough for your project as you can still successfully see that a dog was present in the image. Knowing that the cables caused a false positive hit, we might go back with extra training data to get a better model. Let's say we do that and end up with something like this. We still see 3 instances of the dog class. However, with some math, we can determine that bounding boxes of the same class are overlapping and assume that it must be one large object. We can then find the extents of these bounding boxes to create a larger, more inclusive bounding box. You could average the individual classifications together to get some kind of total confidence score for the detected object. However, this might not work if you had multiple instances of dog next to each other. Note that this method might think overlapping objects are a single object. As you can see, this is a basic approach to doing object detection, but it has a lot of problems. We'll examine more advanced techniques for handling overlapping objects later. Something else you can do is resize the image under the window to the expected resolution of the model's input. For example, maybe we take a bigger section that's 96 by 96 and resize it to 48 by 48 before performing inference. This would keep inference fast and we could scan larger sections of the image. It also might allow us to look for dog objects that are closer to the camera. However, it might miss dog objects that are farther away as the model was not trained on images with this scale. While it might allow us to highlight the dog without computing the extents of several bounding boxes, we run the risk of missing the dog altogether if the stride is too high, the dog is too far away, or if the model is not picking out the correct features due to the resizing operation. Even with a small overlap as shown here, we'd still need to perform 48 inferences per still image. And I'd still need to drop the right and bottom edges without doing some sort of padding or less than normal stride amount for the final windows along the edges. Let's say we have a fairly small model that can perform inference in 100 milliseconds, and we don't need to resize our windows. We would still need to spend around 4.8 seconds per image to locate our object. That would give us about 0.208 frames per second if we wanted to do this on a live video feed. Your project might be fine with such a low frame rate, such as if you just needed to check for the presence of a person or animal every minute or so. However, this assumes that we can find what we're looking for in the frame using a square bounding box. Let's say we're working on a self-driving car that needs to watch for pedestrians and other cars. These square search boxes would only be capable of covering a portion of the object in question. Even if the classifier identified the piece as belonging to a person or car, we'd still have to combine them in some way to denote something as just one object rather than several. That can be a tricky problem. One option is to scan the image with a variety of window sizes ranging from small to large. While this might help spot single instances better, you run into 2 issues. It's hard to determine the exact location of tall or flat objects. For example, is the identified person in the middle, left, or right of the bounding box shown? You would not be able to tell if you just got the coordinates and size of the bounding box. It also means many more inferences need to be performed to scan the image with different window sizes. Taking this a step further, what if we scanned the image with a variety of bounding box shapes and sizes? I've removed the potential boxes for the car as it only cluttered the image. Here, each location, or every few pixels, could be scanned with 6 or more differently shaped windows. The area under the window could be resized and skewed as necessary to match the input dimensions of the convolutional neural network. The network would be trained to know how to work with scaled images like this. From here, we could select the bounding box with the highest score for that object. Ideally, we would end up with something like this to predict the location of our pedestrian. However, as you probably guessed, this is incredibly time-intensive for both training and inference. Instead of sliding many windows over the same image, forcing us to perform inference hundreds or even thousands of times, what if we used another algorithm to propose possible windows for us? This might be a clustering algorithm that groups similar pixels together, or even another convolutional neural network that picks out what it thinks are interesting areas in the input image. Note that they may or may not contain objects. They're just proposed windows that contain something interesting. We then send these windows to our convolutional neural network for classification. This process of identifying potential regions of interest is known as region proposal. Using a convolutional neural network to perform region proposal is known as a region proposal network. These areas are known as regions of interest. Hopefully, our classifier, which we trained to identify vehicles and people, would be able to correctly identify the cars and pedestrians in this image. We'd combine or pick the best window for our bounding boxes and end up with something like this. This saves us a lot of time over the sliding window method to identify objects in an image. Region proposal as a way to feed an image classifier forms the basis for the region-based convolutional neural network model, which we'll look at in a future lecture. Even though object detection methods may have many different parts, we can treat them as a single machine learning model. You can often train some or all of its parts during the training step. The ultimate goal of these object detection models is to locate and classify all of the objects of interest in the photo. For example, let's say I trained this model to identify my dog, his tug toy, and his ball. The output of such a model will often look something like this. You'll get a list of 0 or more objects where each object contains the predicted label and information about the bounding box. If you're working with Python, this might be a list of Python objects you'll have to loop through, or it could be something like a JSON string. The XY location might be the center of the box, or it could be the top left. You'll have to read the documentation for whichever model you're using to determine that. The class prediction will likely come with a probability score from the softmax output. With this information, we can then draw the predicted boxes on the image. We could also use the X and Y information to perform some task, like shine a laser for a cat to play with, or move a camera on a servo to face a particular object. The width and height of the bounding box might also provide some insights into how close an object is to the camera, assuming we have some information about the size of that object. There are a number of popular models that perform object detection like this. These models can be very complicated, and so the inner working details of them are outside the scope of this course. However, in a future lecture, we'll briefly go over a few of the models and demonstrate how to use one of them in Edge Impulse. To go over some performance metrics, you'll want to have a basic understanding of these metrics in order to evaluate the different models that are out there. In the first course, we introduced the concept of a confusion matrix and how we can use it to calculate a number of metrics. The confusion matrix is usually filled out with predicted and actual label counts from the validation or test set. Here, let's say that I'm only looking at the metrics for the dog class, as I'm evaluating a model that tries to detect any dog, ball, or tug toy items in an image. If you recall from that first course, we can calculate the precision score for one class by dividing the number of true positives by the sum of the true positives and false positives. With that, we're trying to get a measure of the percentage of positive predictions that was actually correct. Another popular metric is recall, where we calculate the proportion of actual positives that was identified correctly. To get that, we divide the number of true positives by the sum of the true positives and false negatives. Something else we covered in that first course was the idea of setting a threshold for the output confidence score of a particular class in order to label the class positively or negatively. You often find a threshold of 0.5 to start. For example, if our model gives us a confidence score of 0.5 or higher for the dog class, then we would assign the label dog to that item, which would be a single region of interest taken from a larger image. In many machine learning systems, you won't often find a clean divide between the different labels, and you'll end up with some false positives and false negatives regardless of what threshold you choose. With this threshold, we can calculate the precision and recall values using the given number of true positive, and false negative results. We can then plot that point on a graph of recall versus precision. As you move the threshold up, you generally expect the number of true positives to decrease as well as the number of false positives. However, this also means you gain more false negatives. We can then calculate a new set of precision and recall values with this threshold. With a smaller set of false positives, you generally expect precision to be really good, but your recall will be terrible as you have a lot of false negatives. That might give us something like this on the precision recall plot. As you lower the threshold, you generally expect the number of true positives to increase while decreasing the number of false negatives. However, it also means you see more false positives. From this, we expect the precision to be low but the recall to be high, so we might end up with a point like this on the curve. We would continue sliding the threshold around between 0 and 1 and calculating the various precision and recall scores. We plot all of them on a precision recall curve and we might get something like this. Note that this is not the same as the receiver operating characteristic curve that we saw in the first course, as that plot uses true positive rate and false positive rate instead of precision and recall. After plotting all of the precision and recall points, we would end up with a curve like this. From here, we can calculate the average precision for our dog class. The formal definition of average precision is the area under our precision recall curve, which requires computing the integral of the plot. This would give us a number between 0 and 1, and the closer to 1, the better the model is at predicting the dog class with few false positives and few false negatives. However, because this line was measured, it's likely impossible or nearly impossible to get a good mathematical equation to describe it, and even more unlikely that you'd be able to compute the integral. As a result, a few papers describe methods to sample points along the curve and compute the average to get an approximation of the average precision. One popular method is detailed in the Pascal Visual Object Classes Challenge paper published in 2009. Here, 11 precision values are sampled that are taken from equally spaced points along the recall axis. These precision scores are added together and divided by 11 to give us an approximation of the average precision score. Once again, this is a number between 0 and 1, where 1 indicates a model with perfect or near perfect classification. You might see other ways used to approximate the average precision score, but this 11-point method seems to be one of the most popular. Remember that this is only for our dog class. We would need to compute the average precision scores for the other classes as well if we're trying to judge the total effectiveness of the model. We'll go over a way to combine those scores, but let's talk about how this works with object detection first, as we've only been talking about classification problems so far. When creating your training, validation, and test datasets, you will need to hand draw bounding boxes and label each of the associated objects. Let's say that this is one such example in my test set, and I've drawn the bounding boxes shown here. Bounding box information is usually not stored in the image itself. Rather, you'll often find a separate file that contains information about the bounding boxes. There could be one text file per image or one large file that associates image files with their respective bounding boxes and object labels. We run this image without the ground truth bounding box information through our object detection model, and the model gives us these boxes and labels as predictions. An object detector's classifier will have a non-object class that it is capable of predicting, which I'll call background. You will generally not get background class predictions as output from the model, as this would be every region of interest that was not classified as containing one of our desired labels, and, as a result, would have a large imbalance in labels favoring the background class, which might influence our recall and precision scores. Rather, we can check label accuracy by comparing the predicted classes to the ones noted in the ground truth bounding boxes. That provides us with a simple accuracy score, much like we've seen for other classification problems, and we don't need to take the background class into account. For example, as the ball object was not detected, that would be a false negative. The toy box is obviously not covering enough of the toy object. Measuring how closely the predicted bounding boxes match our ground truth boxes requires a little math. One popular way to measure the success of bounding box predictions is to use the intersection over union, or IOU formula. The intersection is a measure of the area that the predicted bounding box overlaps with the ground truth box. This could be the number of pixels, width and height in inches, and so on. The area doesn't have to be rectangular if you're working with a non-standard bounding box shape. The union is the area under both boxes if you combine them into one shape. You compute the IOU by dividing the area of the overlap by the total area of the union. This is a ratio and gives you a score between 0 and 1. 0 means that there is no overlap and that the predicted box isn't touching any area of the ground truth box. 1 means that the predicted box perfectly overlaps the ground truth box. From here, you can set a threshold as to whether you count the predicted box as being good enough to detect the intended object. A common IOU threshold for models is 0.5, but you may also see 0.7 sometimes. So an object is considered detected if there is an IOU score at or above 0.5 when comparing the predicted bounding box to the ground truth bounding box. Trying to get an IOU score of 1 for every predicted bounding box in an image is a goal of many object detection models, and may even be used as a loss function during training for some models. Let's go back to our image example. Here, the detected dog object might have an IOU of something like 0.9. If we set the IOU threshold to 0.5, this would be considered a true positive detection and classification. However, let's say our toy box has an IOU of only 0.2. As a result, this prediction would be considered a false positive. Because the ball object was not detected at all, but there was a ground truth label for it, this would be a false negative. True negatives are all the parts of the image where we detected no objects and there were no ground truth objects listed. Because there are a lot of true negatives in most object detection systems, we generally ignore this metric while focusing on precision and recall. Let's go back to our precision recall curve. We would only count a detection as a true positive if the IOU value between that prediction and the ground truth label was at or over 0.5. Because this IOU threshold would affect our precision and recall values, we can keep it constant for now. Remember that this is a plot from the perspective of just one of our classes. We would need to generate precision recall curves for all the other classes that our model is capable of identifying. In this case, we would create a precision recall curve for the ball as well as for the tug toy, and they might look something like this. From there, we can introduce the concept of the mean average precision score, or MAP. All we need to do is calculate the average precision scores for each of the classes and then average them together. Note once again that this is still assuming our IOU threshold is 0.5. Using a single IOU threshold might give you a good enough MAP score. The Pascal VOC 2007 challenge used an MAP value with a single IOU threshold of 0.5 for its scoring system. Often you will see MAP scores reported with a single IOU threshold of 0.5 like this. Let's go back to looking at the precision recall curve of just the dog class for a moment. If we vary the IOU threshold, then we would expect the curve to change. Generally, as you increase the IOU threshold, the model has to be more precise in its bounding box location to be counted as a true positive. As a result, you would expect the average precision, or the area under the curve, to decrease. You might end up with something like this for the dog class. The Coco 2017 challenge introduced a new scoring metric where the mean average precision was now an average of all the mean average precision values over 10 different IOU thresholds, ranging from 0.5 to 0.95. In other words, all average precision scores from all classes and a set of IOU thresholds were averaged together. This method rewarded models that were better at precise localization of the objects in the images. However, you'll still often find that many MAP scores assume an IOU threshold of 0.5 as shown in the top equation. I hope that this has helped you get an understanding of how the mean average precision is calculated, as it's one of the most popular scoring methods used when comparing object detection models. Previously, we looked at a brute force method of locating objects in an image by sliding a window across the image and then performing inference on each of the sub-images underneath that window. Now, let's look at a few models that attempt to do all of that much more quickly and efficiently. We saw that instead of sliding differently shaped windows across an image, we could use some other algorithm to propose various regions of interest in that image. This forms the basis for the region-based convolutional neural network, or RCNN, first proposed by UC Berkeley researchers in 2014. Here is the original RCNN paper. I'll make sure to include a link to it in the recommended reading section if you'd like to dig into it, but it can be fairly complex. The first figure does a great job at explaining how the proposed RCNN model works. It combines several methods to produce this object detection structure. It first proposes around 2,000 regions of interest in an image. These regions are warped or scaled to match the expected input of the convolutional neural network, and then inference is performed on all of these proposed regions. The region proposal method is not specified in the paper, but they offer several ideas on what you might use, such as selective search or constrained parametric min-cuts. We won't get into these methods, but know that RCNN was a very important breakthrough in solving object detection problems. The other interesting part of RCNN was the use of a regression model to better predict bounding boxes. It would learn how much to vary the XY coordinates and width and height measurements of the box based on the supplied proposed region and ground truth labels. My dog enjoys playing tug and fetch, and he will sometimes bring me either his toy or ball depending on which one he wants to play with. Let's say I want to train a model that identifies my dog, his tug toy, and his favorite fetch ball. This is a slightly silly way to test object detection, but it's a fun way to see how well I can pick out 3 different objects on an embedded system. Note that going forward, and at least for the time being, you will need to use color images. Many of the popular object detection models rely on color information to help determine regions of interest or to make object classifications. You can technically use grayscale images, but you'll need to find a way to copy the grayscale array to each red, green, and blue arrays. A more useful application might be something like this. Edge Impulse has been working with researchers to track elephant movements in the wild. Part of this also includes watching for poachers to help protect the animals. Cameras could be set up and alert authorities whenever an elephant and human are in close proximity. Embedded object detection would allow us to do this. You could also set something up to notify you if there's a person too close to a package on your porch. This might alert you of a new delivery or a possible theft. But back to our RCNN example. Here is the basic structure of the model. A region proposal algorithm finds around 2,000 sub-image portions that are fed to a convolutional neural network. Note that the CNN used here is just for feature extraction. In the original RCNN paper, the features are fed to a support vector machine, or SVM, instead of a densely connected neural network for classification. The output of this part of the model is a prediction of the class of that particular region of interest. Note that the region could contain just background, so an extra class is added to denote that the region does not contain one of our desired classes. The location information of the regions along with the feature maps and class predictions are fed to a regression model that tells us how we should update the location and shape of the bounding boxes. dx and dy give us how far horizontally and vertically we need to move the bounding box. dw and dh are how much we should adjust the bounding box's width and height from the original region of interest proposal. This information should ideally give us a much better idea of where to draw the bounding box rather than relying solely on the original region of interest location. The biggest problem with this architecture is that once you've identified all possible regions of interest, you still need to perform feature extraction and classification on each region. This could mean up to 2,000 runs of the right side of the model shown here. In 2015, a Microsoft researcher proposed a modified version of RCNN called Fast RCNN. Here, the features were extracted separately using a convolutional neural network. This would create a feature map like we've seen previously. Region proposal would still be done on the same input image using a method like selective search. However, the region information is used to extract sections of the feature map rather than the original image. A method called region of interest pooling takes this information, combines features as necessary, and generates smaller feature maps with all the same size. These new feature sets are passed through a few fully connected or dense neural network layers and then flattened to create one-dimensional vectors. This information is sent to two different dense neural networks. The first provides the classification of the pooled feature subsection, and the second performs regression to provide a better location and shape of the bounding box. The information we get out of this model is the same as RCNN, but it's much faster, as we no longer need to compute new feature maps with convolutional layers for each proposed region. A year later, researchers proposed the faster RCNN model. Instead of performing region proposal on the input image, the model does region proposal on the feature map instead. They introduced the concept of a region proposal network, which is a neural network that can output a series of boxes containing regions of interest along with their objectness score. This score is an indication of how much the network believes there is an object in the proposed region. These regions are used by the ROI pooling layer to create a series of feature maps with the same size, just like before. The rest of the model works just like fast RCNN to output object classifications and bounding box locations. Note that the convolutional neural network that acts as a feature extractor could be the feature extractor portion from another popular classifier architecture like VGG19 or MobileNet. We can even use pre-trained weights from those networks to allow us to do transfer learning on the rest of the model. The big issue is that even though this architecture is faster by doing region proposals on the feature map instead of the images, we still need to perform full classification on each proposed region. In 2016, the same year that faster RCNN was proposed, a different group of researchers put forth a new type of architecture that didn't rely on region proposals or multiple classification steps on those regions. In essence, they used the location information embedded in varying sized feature maps to locate objects in the input image. They called this approach the single-shot multi-box detector, or SSD for short. A known good convolutional neural network like VGG19 or MobileNet would be the feature extractor for this model. Like with faster RCNN, you would need to drop the classifier portion of the network and just keep the convolutional layers, which ultimately produce a series of feature maps with the most salient features highlighted. This feature extractor would form what's known as the backbone of the model. More convolution layers follow this backbone that continue to reduce the size of the output feature map. Each of these feature maps works as a sort of localization grid. Each cell is used as a center point for multiple anchor boxes with different aspect ratios that are used to match with objects in the feature map. As the feature maps get smaller, the grid cells and corresponding anchor boxes increase in size relative to the input image. This helps the model identify objects of varying shapes and sizes in the frame. Each output series of feature maps from the convolution layers shown in blue along with the feature maps generated by the backbone CNN are fed to convolutional classifiers known as heads shown in green on the right side. These heads produce a series of classifications for each of the default anchor boxes. Each head also contains a regression model used to update the XY coordinates and width and height of the default anchor box to create a bounding box. All these predictions go through a non-maximum suppression step, which we'll talk about in a second. The output is a list of bounding box objects along with their associated class predictions. Without the region proposal step used in the previous models, the SSD loses some of its accuracy. However, the SSD architecture is extremely fast as it can produce a series of object predictions with a single forward pass, which is where it gets the name single shot. SSDs are well suited for mobile and embedded applications because of their speed and computational efficiency, even if it means they're not quite as accurate. Because SSD outputs many different classifications in a single pass, we need a way to deal with potential overlapping bounding boxes. That's where non-maximum suppression comes in. Let's say we have a series of bounding boxes for the dog label like this. Any classifications below a threshold have already been filtered out. So we're only dealing with boxes that have over, say, a 0.5 confidence score. Even then, we still have several boxes that overlap on the same object. To start, we select the predicted bounding box with the highest confidence score, which is 0.92 in this example. We then calculate the intersection over union score for each box that intersects with the highest confidence box. Finally, any box with an IOU score over some threshold is removed. You'll often find an IOU threshold of around 0.6 for non-max suppression. What we're left with should be the best bounding box for the object in question. This is repeated for all classes and all non-intersecting boxes of the same class. The idea is that we should ultimately get an output of bounding boxes and confidence scores that uniquely identify the various objects in the input image. The hope is that objects can be of any shape or size and any distance from the camera. However, SSD struggles with very small objects in the frame as there are simply not enough pixels to sufficiently describe that object. Also, default anchor boxes may not be small enough to catch some objects. The only way to deal with that right now is to increase the size of the input image and retrain your model to work with higher resolution images. Also note that many of these object detection models rely on pre-trained backbone networks like MobileNet. These networks were trained on a known good image set like ImageNet or COCO. However, if you're trying to identify objects that were not represented in the dataset used for pre-training, you might run into problems as the convolutional filters were never trained to look for your particular custom object. For example, I don't think my specific dog tug toy is in the dataset, so I expect an SSD model pre-trained on ImageNet or COCO to struggle finding this object if I only rely on transfer learning. The ball might also prove difficult as it's rather small with such a low resolution. Here is a pre-trained SSD model with a MobileNet version 1 backbone. The MobileNet feature extractor can be seen at the top of the model in Netron. You can see where the output of this series of convolution layers goes to a pair of convolution heads that give us a set of object classifications and bounding box locations. The SSD convolution layers also feed into similar pairs of convolution heads that give the same kind of object detection predictions. All of these predictions are fed into a post-processing step that performs non-maximum suppression and combines the predictions into a list of object labels and box locations. The following paper from 2017 gives an overview of various object detection models at the time. Figure 2 gives a great depiction of how well the various detectors performed using mean average precision as the scoring system. We looked at faster RCNN and SSD, and you can see various versions of those detectors with different feature extractor backbones. SSD with a MobileNet version 1 backbone is not very accurate compared to some of the others, but it's one of the fastest, which makes it popular for embedded systems. There are other models out there that we didn't cover, like RFCN, which stands for Region-Based Fully Connected Network. Note that the models here were trained on the COCO image dataset with non-maximum suppression IOU threshold set to 0.6. The mean average precision score is taken as an average over IOU thresholds ranging from 0.5 to 0.95. We can make improvements to SSD by using more advanced backbones like MobileNet version 2. Additionally, we can introduce other concepts like feature pyramid network or FPN. The blue squares in these images are the feature maps that are generated from one or more convolutional layers. The top left shows how we can resize images, run them through a series of convolutional filters, and then use those feature maps to make predictions about the contents of the images. We see something similar with B in the top right. However, here we use convolutional layers that reduce the dimensions of each subsequent feature map, and we only make our predictions with that final layer. This is how our traditional convolutional neural network classifier works. We can combine this with a region proposal system to get an object detector, just like we saw with RCNN. Next, we have the pyramidal feature hierarchy, which predicts features based on all of the intermediate feature maps. This is how our SSD model works. The paper proposes the image given by D, which is the feature pyramid network. In this, a new series of convolutional layers are introduced that actually upsample the smaller feature maps. Feature maps from the first set of layers are combined with the upsampled feature maps before being sent to the classifier heads. This has the effect of expanding salient features from the filtered feature maps into higher resolution maps with the intent of raising average precision and small object detection. Here is a look at a single-shot detector I trained to look for instances of dog, ball, and tug toy. The top part is the MobileNet version 2 backbone, which contains a series of residual blocks. Some of the feature maps from these residual networks are copied to sections below, which make up the feature pyramid network. Here you can see that 10 by 10 maps from this convolution layer are then continuously upsampled using more convolution. Feature maps from earlier in the network are added to these upsampled feature maps, which go all the way up to 40 by 40. These combined feature maps are sent to prediction heads, and the smaller feature maps are also sent to prediction heads. The output of these heads are combined to give us a list of detected objects and their bounding boxes after a round of non-maximum suppression. YOLO, or You Only Look Once, is another popular model that we didn't cover. This paper from 2020 covers version 4 of the YOLO model and introduces some advanced techniques that make it faster and more accurate. At the bottom of the paper, you can see a chart comparing YOLO to other models, including SSD. You can see how it compares to SSD and other object detection models. Note that the size and speed of the model will depend on the backbone used, as well as other features and layers in the model. Both SSD and YOLO are popular for their small size and speed, and they are getting more accurate with each revision. Don't worry if much of this seems really confusing. This was supposed to be a very broad overview of the last few years of research into object detection models. Now that we've briefly seen how object detection models work, let's train our own in Edge Impulse. Object detection models take up a lot more space and require a lot more computation power than simple image classification networks. As a result, you need a more powerful board when you go to deploy the model. I recommend the Raspberry Pi 4 with the Pi camera for the project in this module. TensorFlow Lite for microcontrollers does not support some of the operations required at the time this course was released. So, while the OpenMV H7 Plus might have enough memory and processing power to run an object detection model, it simply won't work for this project right now. If and when support for object detection models is added to OpenMV, I will update the materials in the course to include it. To collect a dataset, you'll want to capture a bunch of images that contain the objects you're trying to look for. You'll also want to have them in PNG format, as that's what Edge Impulse works with. In this case, I am trying to train an object detector that looks for my dog, his tug toy, or a ball, as you can see in this image. The idea is that every now and then my dog brings me one of these toys, whether it's a ball or the tug toy that's the little red figure 8, to me when he wants to play, and I want to train a detector that lets me know that the dog is near one of these toys and possibly wants to play. I don't know how ultimately useful this is, but feel free to train your own detector for things like people, other animals, cars, fruits, other foods, or maybe road signs if you're trying to make something like a self-driving car. Notice that these images are full color. The object detection model that we're going to be using expects full color models, not grayscale. So don't try to save on space by converting all your images to grayscale. They need to be 320 by 320 pixels, as that's what the model expects. You can have Edge Impulse crop or resize your images, but I like to capture things in the exact format that's expected by the model. So everything I've collected is 320 by 320, and I have a variety of different rooms, backgrounds, lighting, angles, the dog's in different positions, the toys and the ball are in different positions. These help to train the model to look for the objects in various positions and lighting conditions. I also try to include a variety of things like just the toy by itself, the toy and the dog by itself, or maybe all three in the frame, which you can see in this image here. You'll want to have about 50 instances of each object. That doesn't mean you'll have a total of 150 images if you have 3 classes, but spread across these images, you'll want to have about 50 samples of those objects. If you have 50 images and each of those images contain your 3 objects, then you only need 50 images. If you're working with the OpenMV, I recommend using the image capture script I gave you earlier in the course. Here, you'll want to keep it as RGB 565, which is color rather than grayscale. And you'll want to change the width of the frame and height of the frame to 320 by 320. Additionally, you need to adjust the frame size, as QVGA captures things in 320 by 240, and so we're just going to set this to VGA, and then we're going to crop down to 320 by 320. When you run this, you should see a color image show up in your viewfinder, and after about 3 seconds, it will capture an image and store it on the SD card of your OpenMV. From there, just take out all of your images and store them somewhere on your computer so that you can upload them to Edge Impulse. Note that if you're capturing from OpenMV, everything's probably going to be in BMP format, so you'll want to convert it to PNG. Finally, if you're doing things with the Raspberry Pi, I recommend running the PyCam capture script. Here, you'll want to change the image width to 320 and the image height to 320. From there, just run this script on your Raspberry Pi and it should capture color images in 320 by 320 resolution. Then just copy those images from your Pi, make sure they contain the objects you intend to look for, and we're going to upload those to Edge Impulse. Head to Edge Impulse, log into your account, and let's create a new project. I'm going to call this one Ball Dog Toy Detection. Feel free to be a little more creative than me in your naming schemes, but this at least lets me know what kind of things I'm looking for. From here, I'm going to exit out of the pop-up screen. On your dashboard, you're going to need to scroll down and head to Project Info. There, look for Labeling Method, and we're going to change this to bounding boxes, as that's going to change how we label our items. Note that we're going to be labeling or providing ground truth bounding boxes in Edge Impulse rather than using a third-party program or trying to do it manually by creating a file with a bunch of labels and bounding box information. From here, head to Data Acquisition, and then click to upload your files. You're going to want to leave it as automatically split between training and testing and infer the label from the file name. This does not really apply since we're going to be making bounding boxes on each of the images. Select Choose Files, and find where you've created your data set. Highlight all of your images. I do recommend going through these to make sure that your objects are clearly visible. As soon as an object moves out of the frame, it might make it a little harder to detect unless that's something you're looking for where you're okay detecting part of an object in the image. Let's upload these. We'll click to begin upload and wait just a second while it uploads all of the images. From there, head back into Data Acquisition and you should see a new tab that's appeared called Labeling Queue. Click on that and you can start labeling your objects. All you'll do is click and drag to create a bounding box and you'll enter a label. Here I've got dog, and I can move the bounding box around. You'll want to make sure that it barely captures your object in its entirety without leaving too much extra space around it. And I'm going to move it over, and then I'm going to draw another bounding box for my next object, which I will label as toy. Here I'm going to move the bounding box again so it's just capturing the object, and I'm going to adjust its size, and I'm going to click Save Labels. In the next screen, I'm going to do the same thing. I'm going to find where my objects are, and I'm going to move my bounding boxes around. I'm going to do the same thing with dog. Resize that one, click Save Labels, and continue. You'll want to keep doing this for all of your images and for all of the objects in your images. This might take some time, so be patient as you go through it. When you're done, I recommend going back into training data, and you can look through all of your images here. You can see the labels that are associated with the objects in those images, and you can see the number of labels for objects in those images up in the right corner here. You can also do the same with your test data. If you made a mistake and you need to relabel something, you can click on the drop-down menu on that image and select Edit Labels. This will bring you to a new screen where you can move the labels around, add new labels, change the label names, and so on. I don't need to update this, so I'm just going to X out of that. You can also get a preview of where all the labels are on your objects, so I recommend taking a look at those to make sure they're good. If you missed any, go back and redo them. When we're done, head to Impulse Design. Take a note of the text here. For object detection, at least for right now, we must use input image sizes of 320 by 320, so I'm going to leave this to be the default. If you don't have it already, you'll want to add an image processing block, And you may not have anything here, so you'll want to add object detection images. Save your impulse, and then head over to your feature extraction tab. We want to keep the color depth at RGB because the object detection model expects color images. It will not work with grayscale, at least at this time. Save these parameters, and then click Generate Features. This should not do a whole lot other than maybe tagging the images and creating a file or something that contains all of the bounding box information. It additionally compresses the dimensions of the various objects found in the images so we can see them in the Feature Explorer here. You should see some decent separation among the object classes. However, I don't see a whole lot between the toy and the ball, which means I'm not sure that this model is going to work very well, but we will see. From there, head to your Object Detection tab. I like to increase the number of cycles. I find that 25 is a little low to work with. Something in the 50 to 100 range works pretty well for me. I'm going to leave the learning rate and the score threshold alone for now. I don't have many options at this moment. There's only one model that Edge Impulse supports at this time for object detection, and that is a single-shot multi-box detection, or SSD, architecture with a MobileNet version 2 backbone used for feature extraction. It also contains a feature pyramid network, and that's all converted to a TensorFlow Lite model when it's done being trained. In this case, we are using transfer learning, so it should train a lot faster in a matter of minutes rather than hours or even days. Do note that Edge Impulse says it's able to locate up to 10 objects with an image, so there is a limit to the number of objects it can detect, at least on this version of the model. We are going to go ahead and use that model, and let's begin our training. So just click Start Training. In a previous lecture, I talked about how the backbone for this SSD model can be pre-trained on a known good set of images. In this case, the MobileNet v2 backbone is trained on the Coco set of images. If this set does not contain some of the things that I'm looking for, like maybe the tug toy is not in that training set, the filter parameters may have a hard time picking it out, whereas dog is likely one of the images in that training set, so the filter parameters kind of know what to look for, and there's a lot of complexity that goes into animals. They have repeating patterns like fur, they have legs, they've got faces, ears, eyes, nose, mouth, maybe a tail. There are things that the parameters can look for to help determine that that is a particular animal, like dog. So I expect this model is going to pick out my dog a lot more easily than it does, say, the tug toy. The ball is an interesting one. Simply because the ball is a very simple shape, I would figure that some of the simple lines that go into creating the ball, at least when it comes to creating an image of a ball, should be pretty simple and straightforward. However, it's a weird color, which I'm not sure matters in this case, but the idea of a basic circle might be actually tough for something that's looking for more complex features. We'll see when this is done. The other thing that concerns me is that at least for 320 by 320 resolution photos, the ball is relatively small. I think it's on the order of 10 by 10 or maybe 20 by 20 pixels, which going into the network is going to be a relatively low number of features coming out on the other side of all those convolution filters. However, that feature pyramid network, that FPN portion of the SSD, should allow the network to work with smaller objects. We'll see if it works for the ball object in this case. With training done, we can look at the model's performance. Here you can see that it scores about a 73.1% with the validation set, and that's with the 8-bit quantized model. We can also look at the float32, but you'll notice that it takes a little more flash. In this case, the precision goes up to about 85%. Generally, when working with a lot of these embedded systems, you'll want to use the quantized model where possible. The other thing that I recommend doing is going to Model Testing, and then clicking Classify All. Wait for just a moment while it tries to detect all of the objects in the test dataset. As you can see, it's only performing at about a 67%, which is not great. I recommend taking a look through your test dataset to see where the model is failing. In this case, it's looking like it's failing on ball and toy. We can select Show Classification, and I'm going to do that for a number of these images where it failed to label one of the objects. So let's open these up. Once you have them open, you can see where the ground truth labels occur. In this case, it looks like the model tried to classify the ball with an 83% confidence. However, it completely missed the toy, and that's likely because the toy was shown on its side here. And if we keep looking at the images, it missed the ball when the ball was next to the dog. Once again, it missed the ball when the ball was next to the dog. It did successfully classify the toy object here. It's looking like the ball is not classified whenever the ball is next to my dog's light-colored fur. And that could just be because the feature extractor isn't seeing any edges, or it's considering it to be part of the dog. I'm not exactly sure what's going on, but this does appear to be a common problem. And here, it just completely misses the toy, even though the toy is in plain view. It misses the toy, but the ball was found. The ball wasn't near his light-colored fur, but it was on this light-colored piece of rug. But it did miss the toy. That's interesting. Once again, it missed the toy, and this might be too small of an object because it's so far away. It looks like the model is struggling to find the toy, and once again, the toy is missed, but it did double classify the dog, which is not great. It looks like the non-maximum suppression failed here as it considered this 0.54 object to be the dog, even though that is not correct. From what I could tell, it struggles with the toy object, and it struggles sometimes when the ball is next to light-colored objects like my dog's fur. The toy object I'm not particularly surprised about, simply because I don't think it's something that was in the original training set. So I'm asking the model to try to identify the toy using filters that weren't trained on something that looks like this toy. That is something important I recommend keeping in mind, that you should probably stick to objects that were part of that original training set and using those as a starting point for what kind of objects you should be looking for. You can get away with training new objects that aren't in those original classifications, but the model might struggle to find those. When you're happy with the results, and in this case, I could probably go back and train a bunch of images with the ball next to my dog in various positions in order to try to get the object detection to find the ball in those cases. And an option for the toy might be I have to use a different toy, one that looks like an object that was part of the original training set classification scheme, or I might have to train that backbone from scratch, which at this time, Edge Impulse does not support, so that would be a little more involved. When you're done, head down to Deployment, and you can download a library containing all of the feature extraction and model information ready to be deployed to your system of choice. And in this case, remember that object detection takes a lot more RAM and flash memory, so you will want to use a very powerful microcontroller or something like a single board computer. Now that we have a trained object detection model, let's download it onto our Raspberry Pi and then use it for live inference. To start, we'll want to make a new project folder. I'm going to call mine Ball Dog Toy Detection, and I'm going to go into that directory. Once again, I'm going to run the Edge Impulse Linux runner with the clean parameter that allows me to select a new project and then tell it to download the model file from my object detection project. Sign in with your username and your password. You'll want to select your object detection project, and then the tool should automatically download your model file. From there, you can check that the file does appear in your Linux file system. To start, we're going to import some Python packages and modules. As we've done before, we're going to need OS, System Time, OpenCV, the two PyCamera libraries, as well as the Edge Impulse runner. Notice here that we're using specifically the image runner, which is different from what we saw in the dense neural network, as this one allows us to extract features from images. From there, we're going to need to load in our model file that we just downloaded, and we're going to need to set the resolution, width, and height, which I will keep to 320 by 320, which is what the model expects. As we've done before, we're going to load the model file, and then we're going to initialize it. If this initialization process causes any problems, we'll throw an exception, print it out to the console, and exit the program. Because object detection is normally very computationally expensive, I'm going to keep track of the frames per second and print it to the preview window so we can see how quickly this whole thing is running. Next, I'm going to start the Pi camera, and as I've mentioned before, you're welcome to try this with a webcam, but this code is going to be a little different since we're not using the Pi camera library. Webcams and Linux have traditionally had a somewhat difficult history where there weren't a lot of drivers that supported webcams. I think that's different in this day and age. However, because there are so many webcams out there, I won't be able to help you debug whatever particular version of USB web camera that you're using. So I recommend using the Pi camera if you're taking this course. I should be able to help you debug any problems you might have with it. From there, we'll configure the camera with 320 by 320 resolution. We're going to set up a for loop that essentially runs forever that gives us a new frame in this frame variable each time it runs, and that's coming directly from the Pi camera. From there, we need to get a timestamp of the current time so that we can print out the frames per second onto the preview. We're then going to get a NumPy array from this frame variable. With that, we can convert it into the features that the edge impulse model expects. And to do that, we're going to call the runner object, which comes from our model file that we imported with the image impulse runner. And we're going to call this getFeaturesFromImage function and pass it our NumPy array that represents our image. Remember that this should be an array of pixel values where each pixel is represented by a blue, green, red value between 0 and 255. We should not need to perform any other feature extraction or image manipulation since the image should be in the correct resolution with the correct color and BGR values, which means after we call the getFeaturesFromImage, they should be converted to whatever the edge impulse model expects in this features variable, and we're going to pass that to the runner.classify in order to perform classification using our object detection model. I always like to print out the raw output from this model in order to see how I can look into it or index into it to get the values that I need. If you were to print those to the console, you should see that we get a list of bounding boxes. If there are no bounding boxes, it should just be an empty list, and so this for bbox in bboxes just shouldn't run. Using the information from this bounding box list, we can extract the x and y coordinates as well as the width and height in order to be able to draw our own bounding box on top of the detected object. You can also use this information for whatever embedded system project you are trying to do, like point a laser pointer in front of a cat, throw a ball for a dog, figure out where cars are in an image in order to avoid them, and so on. For testing, I'm just going to draw a bounding box over the detected object. To do that, I'm going to use the OpenCV rectangle function, give it the image where I want to draw that rectangle, and then give it the coordinates of the x and y that were from the original bounding box, that should be the top left corner, and then the bottom right corner given by x1 and y1, which should just be the x value plus the width and the y value plus the height. I'm going to draw these bounding boxes as pure white, so I'm going to use 255, 255, 255, but feel free to, say, assign a new color for each unique label or each unique class so that you can have, say, all dog objects be highlighted in red and all ball objects be highlighted in green. But I will leave that up to you to try. I'm just going to paint everything in white just to make it simple for this script right now. The next thing I'm going to do is draw the object label. I'm going to change this to label, and I'm going to draw the score at the top of the bounding box, so you should be able to see the class that each bounding box should represent, along with the confidence score or probability. To get those, all we do is just call the bounding box that we get from the list of bounding boxes, index in using the label key, and we do the same thing but using the value key. That should give us the class label along with that class's or label's particular confidence score. And we can just print those inside of the bounding box given by the x and y of the bounding box. Finally, even if I don't have any bounding boxes that resulted from inference, I am going to draw the frame rate in frames per second on the frame. This gives me an idea of how quickly this whole thing is running, which includes capturing an image, converting it to the correct features, and then running inference in order to find those bounding boxes. As we've done before, we need to call the imshow or imshow from the OpenCV library, give it the image, and this makes it appear as a preview window with the name frame. To get it to work, we also need to truncate the raw capture from the frame that we saw earlier. This prepares it for the next frame and allows the frame to continually update, giving us something like a video stream. Next, we calculate the frame rate that gets updated on the preview in the next iteration of this for loop, and then give it some way to quit out of the program by pressing the Q key if we have that preview window highlighted. If we do press the Q key on that preview window, we'll want OpenCV to destroy all of the open windows just to create a nice way to clean everything up. Next, I'm going to save this on my Raspberry Pi in my ball dog toy detection folder, as that should have my .eim model file. And I'm going to call it live detection PyCam. Let's save that and now go over to the Raspberry Pi to see if it works. The script that we just wrote should be saved on the Pi, and you can see it here as live detection pycam.py. Now we're going to run it, and I'm going to move my PyCam around to see if it will detect things. As my dog walks around, you can see it is detecting dog correctly for the most part. If he lies down, it's about 0.7. It's picking up the ball every now and then, and it's grabbing the toy, although it looks like it's getting two bounding boxes sometimes for the toy and the dog. When I move the ball, toy, and, well, dog to a farther location, you can see that it still detects the dog decently well. It detects the toy okay, but I'm starting to get about a 0.5 confidence, which means it's starting to lose it, and it's not detecting the ball at all. This just goes to show that smaller objects do not perform very well with this model, even though we had a lot of training data showing the ball farther away. As a result, I recommend using a model like this with such a small resolution for objects that are closer up, or larger in the frame that just take up more of the frame where the model can pick out individual features on that object. However, it is still detecting my dog pretty well. Additionally, you can see that the frame rate is about 1.7, 1.8 frames per second, which is pretty slow, and that's about as good as we're going to get on the Raspberry Pi. If you introduce things like a hardware accelerator, or you switch to something like an NVIDIA Jetson Nano, where you have hardware architectures that accelerate or are designed to run things like neural network, you can expect a better frame rate. However, this is going to be the best we can do for now, but about 2 frames per second is pretty good. I hope this helps you get started training and deploying your own object detection model on something like a single board computer. Let's take a quick look at image segmentation. It's an advanced concept that we won't spend much time on in this course, but I want you to know that it's out there as an active area of research in computer vision. The idea behind image segmentation is to separate each object in an image by examining its individual pixels. As such, each pixel in the image is given a label as belonging to one of the objects. For example, in this photo, we might want to separate the different objects. You'll often see image segmentation outputs as another image with the same dimensions as the input image, but the pixels classified to their respective objects. For example, the laptop is black, the wall is white, the table is yellow, the power cable is red, and the glass is blue. We would want to have a good idea of the individual classes we're looking for when constructing such a model or filter to produce a segmented image. If we were trying to identify keys on a keyboard as opposed to anything else in the image, the output might look a lot different. Object detection gives us bounding boxes with X and Y coordinates. Image segmentation gives us more information about the shapes of the different objects. A bounding box might be good enough, but sometimes you need more information. For example, image segmentation might help medical researchers look for cancerous cells and isolate them from normal cells. In that case, the shape of the cell could be very important in determining its type and exact location. This is an image of cancer cells that have been colorized by the National Institute of Health. Image segmentation could help us identify such cells and give us similar coloration automatically to help identify cancer in patients. This paper combines segmentation with the faster RCNN model to help identify pedestrians more accurately. This is potentially useful in security cameras and self-driving cars. One of the easiest forms of image segmentation you can do is a simple threshold. Convert an image to grayscale and set a threshold value. Any pixel over that value is one color and everything else is another. Assuming my grayscale capacitor image here is stored as a NumPy array in the IMG variable, this code snippet will convert anything less than a value of 145 to white. Everything else will be black. This produces a very basic segmented image of my capacitor. Note that this only works on objects that have a high contrast with their background. You could set up multiple bands of color or grayscale values, but this doesn't work well with objects that have lots of complex shapes and colors against similarly complex backgrounds. Another popular technique is to use k-means clustering to group pixels with similar color values or other features together. However, this only works well when the features are guaranteed to be similar within each class or object. Imagine a person wearing different colors for their shirt and pants. While k-means might pick out the different articles of clothing, it might struggle to see the whole person. In 2015, UC Berkeley researchers proposed something called a fully convolutional network. Here, they used the feature extraction portion of a convolutional network to create a feature map. Note that this section could be something like VGG or MobileNet without the classifier network usually found at the end of the model. This feature extractor is also known as an encoder. The feature map is then sent to another convolution layer that produces an output the same resolution as the original input image. This step is known as a decoder, and it's in charge of assigning a label to each pixel in the output segmented array. What we've been looking at so far is known as semantic segmentation. This is where objects of the same class are given a single value. As we see in Figure 6 of this paper, objects of the same type are highlighted in one color. For example, person, horse, and car are different objects that get the colors pink, magenta, and gray respectively. This type of classification isn't great for determining the number of instances of each object present in an image, but it can tell us where some objects are located. Note that training this model is like training other convolutional neural networks that we've been looking at in this course. The difference is that the ground truth output is a segmented image map where the pixels have been given values that correspond to the object they represent. The idea is that the model's convolutional filters would automatically update their weights during the training process so that an input image like the one on the right would produce an output like the one on the left. Other similar models have been proposed. For example, researchers created this UNet model for doing biomedical image segmentation. Similar to the fully convolutional network, UNet contains an encoder that is much like the convolution layers we've been looking at in the course. An input image goes through a series of convolutional filters and pooling layers to produce a smaller feature map. This feature map then goes through a decoder, which upsamples the feature map to create a segmented image the same size as the original input image. The trick with UNet is that it concatenates feature maps from various stages of the encoder side to same-sized feature maps on the decoder side. Once again, the model outputs a segmented image with the same resolution as the input image. As you can see in the results section, UNet has been successfully used to identify different parts of cells. While there are plenty of models out there that improve on each other when it comes to image segmentation, the last one I want to show you is a model called MaskRCNN, which was proposed in 2018 by the Facebook AI Research Group. MaskRCNN does something a little different than the semantic image segmentation models we were just looking at. It's attempting to do what's called instance segmentation. The output images in Figure 5 do a great job at explaining what this means. As you can see, it's not only doing image segmentation to identify the types of objects and which pixels make up those objects, but it's also doing object detection. This means that it can uniquely identify each object of a class in the image. Instead of just highlighting all the pixels that make up the person class, it can identify the individual instances of the person class. It does this by building on the faster RCNN model. It adds a new mask RCNN system to the faster RCNN model that uses a full convolutional network to create a mask of pixels from each proposed region of interest. From this, the model outputs a class prediction, bounding box, and pixel segmentation for each object found in the image. Don't worry if you didn't fully follow this lecture. Right now, image segmentation is mostly being used in large computers to assist with complex computer vision problems. As a result, it's a little out of scope for our course. However, I fully expect to see image segmentation making its way to embedded systems in the near future. Multi-stage inference requires training and using multiple machine learning models such that the output of one model becomes the input to the next model. Dmitry Maslov from Seed Studio is going to talk about multi-stage inference and give a demonstration using a Raspberry Pi-based platform known as the RE-terminal.
Hello everyone, my name is Dmitry Maslov from Seed Studio and Hardware AI. Let's talk about multi-stage inference. You have already familiarized yourself with object detection and image classification tasks. Multi-stage inference in computer vision most of the time involves a combination of these two. What is the main benefit of using multi-stage inference? Object detection networks in general, and the ones used on embedded devices in particular, are not very good at distinguishing between multiple similar classes of objects. So what we very often do is use object detection network to detect a large class of objects, for example, a face or a car or a dog, and then crop out the image and rescale it, the result of detection, to be fed to image classification network, which gives a much more nuanced output. For example, the emotion on the face, car model, or dog breed. Another popular use case for multi-stage inference is OCR, or optical character recognition. Instead of performing detection of every character in the whole image, which is resource intensive and prone to errors, most often we first detect the text and then recognition is performed on pieces of text cropped out of large image. For this exercise, let's take car model recognition as an example. In Edge Impulse, train a car detector. This should be fairly easy since we are using transfer learning and the base model already was trained to detect cars. So it contains the necessary feature maps. For image recognition model training, we are going to use a subset of Stanford cars dataset with 6 car model classes. I picked 6 classes of cars that I think I will be able to encounter while walking outside here in Shenzhen, China. After training the model and optionally checking the detection and recognition accuracy on pictures that you can take with web camera or find on the internet, let's deploy these 2 models on an embedded device. I have used RE-terminal, a Raspberry Pi 4 compute module-based development board with a touch screen in a sturdy plastic case. It comes in handy while on field trips like the one I'm going to take. Raspberry Pi 4 compute module has the same CPU as Raspberry Pi 4 development board, but has an option to include onboard eMMC memory. The module in RE-terminal has 4 GB of RAM and 32 GB of eMMC. First of all, you'll need to download the models for car detector and car classifier, which you can do by using Edge Impulse Linux Runner. logging first to the project for car detection, and then run the following commands, which is edge impulse Linux runner download car detector .ein, and then logging into your car classifier project, and then you'll need to run clear command, and then you'll need to log into car classifier project and download the model for car classification. Then if you look at the multi-stage inference script, you'll see that it's actually very similar to the scripts for object detection and image classification. Basically, it combines these two. You'll see that the main function of this script is very similar, with the exception that we obviously have two models now. So we're getting the path for detection model, for the classification model, and then creating the context for both of the models at the same time. Then we get the information about the models and print it out. Then we find the suitable web camera here, and then here is for loop that is going to acquire the images from web camera and then return the detection results and the processed image. Then what we do is for each bounding box of the object that we found, we are cropping that bounding box out of the image and then resize it to the classification model input size, and then we performing the inference on that smaller image with the classification model. And then finally we do some printing here, and also I added the draw result function, which obviously does what it says exactly here. It draws the both detection bounding box and the classification result. And you already saw how it works in the previous video. In conclusion, do we really need multi-stage inference? And could object detection model do both detection and fine-grained classification? There are some models that can perform detection and large class size classification pretty well, such as YOLO 9000. Not suitable for running on embedded devices with constrained resources. So for now, multi-stage inference is best technique we have in our computer vision arsenal for this type of application.
Matt Kelsey is a machine learning researcher at Edge Impulse, and he's going to talk to us about his active area of research. By breaking a neural network down into components or layers, we can reuse intermediate outputs from those layers to create a self-supervised learning system.
Hi, my name is Matt. I'm going to do a short talk on reusing representations. So what do I mean by representations? Well, let's go through a quick sort of high-level view of what we often think about machine learning, which is this idea of our goal is to learn these functions f. And the function we're trying to learn takes some sort of input, I'm going to call this x on the left, and tries to map to some sort of output that of interest to us. And when I say representation, I'm sort of thinking about any of the internal sort of features that a network like this or a function like this f may learn along the way. So one particular thing of interest here with these functions is that they're often around compression. So I can think about this function f as going from some high dimensional x, like an image, to some very low dimensional y. Say, for example, I'm trying to do classification where I'm saying, is this one of 10 classes? Now, neural networks have another logical breakdown. We often go by the name of, say for example, layers, where this f is actually composed of many little f's that sort of talk to each other. And the first f is responsible for taking the input x and sort of changing it in some fundamental way that then becomes input to the next this sub-function f. And when I think about representations, I'm thinking about what are these internal sort of structures, the internal views of the data as it gets passed along from this x on the left to the y. Now, a modern neural network with these f's may have many of these layers, 100 plus or more. But for this talk, I want to really talk about one of the ones that's more to the right-hand side. It's one that's getting closer to the output. And as I said, because there may be many of these f's, you can think about the sort of the functions on the left-hand side being maybe 99+% of the entire model as a whole. And this last little bit at the end is just like, you can think of maybe as the last few transformations from whatever this sort of internal encoding that the network has learnt to the final sort of thing of output. So I'm gonna think about it in that way, that when we're training these functions, if we're actually training two functions, one like an encoder, so there's learning this internal representation, and that's this first piece, and that's the bulk of the network. The bulk of the network sort of goes from X down to E, and E has been co-trained like this, jointly trained with this other part to then output this final prediction of what Y might be. And why have I sort of split it like that? Well, there's a lot of ways that are using one part or the other of this sort of decomposition in interesting ways. Probably the most successful and very well-known way is an idea called transfer learning. If I think about starting with a very large data set, B here denotes a very big data set, and I jointly train these two functions, the encoder and then sort of, a part on the end, maybe it's a classifier, a small classifier at the end. Then if I'm a large internet company, I might have trained this very, very large encoder on a lot of data. And why do I care about that as a user, maybe that only has a small amount of data? Well, there's this general adage in machine learning that says the larger the network we need, the more sort of examples of data we need to train it. So if my X here, my small X, is similar to my large X, I can take a bit of a shortcut and I can say, well, let's just reuse the existing encoder that maybe someone has made available to me, and then only train the second piece. And under that general idea, which is true, that the less parameters we need to train, the less data we need, I can sort of, get a good result with only a small amount of data, under the assumption that my input was the same. So if this is a large vision model that's been trained on something like ImageNet, which has a large diversity of sort of natural images, then I should be able to get away with training with a small amount of data. That's a really great thing for me. And this is the common fundamental setup in transfer learning. What this talk is going to be a little bit more about, which I think is really, really interesting, is the next wave of this type of work, which is around this idea of contrastive learning. And in particular, it's talking about this function that we're learning here, E, in the context of other data sets. And I'm going to go through one fundamental thing that allows us to do a lot of what we'll follow. Let's assume we've got a data set, and this is the ith instance of this data set. So I don't know what it could be. Let's say we're doing classification of images into 1 of 10 classes, and this is an image of a tree. So I've got some particular image of a tree, X, and I've got some label that is currently tree. This represents one instance in my data set. What if I had another instance in my data set? I'll call this the jth instance. Again, it would be an image of something and a class. Now, there's a particular interesting thing. Say that for the selection of these I and jth instance, that the Ys were the same. So say they were both trees, for example. Then under this idea that this network is about trying to compress things and smoothly doing it towards the sort of output, then it seems intuitive to say that if these two Ys are the same, say tree, then I would expect at this point of the encoding for the encodings to be like each other. Because if I'm sort of thinking about this second part as being a classifier that needs to sort of operate on this encoding, then if they were both trees, then the encodings need to be the same. So fundamentally, that idea that the encodings need to be the same when the class is the same can hold no matter what the class is. So it's a reasonably strong assumption to make, but an interesting one to say that I can start to use this as a learning objective. I can say, given that two instances are the same class, I want their encodings to be the same without even knowing what the class is. And that's very powerful, and we can use that in a lot of different ways. One of the fundamental ways this is being used now in a lot of the state of art models is this idea that focuses around how augmentation works in images. So let's have a quick review of what that means. There's a really common thing you probably would have seen in image classification or a lot of image networks, where I can take an image like this picture on the left-hand side, and I can, if I'm doing classification, I can take that image and I can do lots of transformations of that image that don't break the idea that the class is still the same. So we might rotate the image, I might do a little bit of a crop, I've changed the color, in this case, saturation, contrast. But the fundamental idea of image augmentation is that I can do all these transformations that put me in a different part of pixel space without fundamentally changing what the salient object class is. So in this case, it would be dog, but by doing all these mutations, I keep it as dog. We can use this idea that I can do image augmentation to make instances of the data where without even knowing what the class is, the class has not changed. Let's concretely talk about that. If I then say, I'm going to take a picture of my dog here, and I'm going to apply 2 random augmentations. And you know, it's a really good thing about this augmentation approach is that it's stochastic. So maybe I've rotated one way, I've rotated the other way, I've changed different amounts of lighting. If I think about these instances of training that I want to feed into a network, if I'm only interested in learning the encoder part, you know, as a pre-step to doing some transfer learning maybe later on, what I can say is these 2 images through the encoder, I want them to be the same. So without even knowing what the original class was, I'm going to say this is going to be part of my learning objective. I want the network, when it's learning this encoding, to when it takes this image and when it takes this image, return the same encoding. Now, I don't actually care where, if I think about this in a spatial sense, and I think about encoding as being a point in space, which is common in say, the embedding view. I don't care where they are, I just want them to be close to each other. Now, we have a bit of dangerous position here. Neural networks are good at optimization, and the optimizer will, you know, nicely degenerate everything to 0. So what I'll actually do commonly in these contrasting cases is to pick another example where I don't want things to be the same. So for example, a picture of this cat. So when I take the cat and I sort of change it, I want this to be an encoding that as an objective is different to the other ones. So I can treat this as, I want these 2, the red and the green, to be the same encoding. I'll treat that as part of a loss function, and at the same time add components to that loss to say that the red and the blue ones should be different. Now I can do this. With instances where I don't know the label, just by saying take any image from a large data set and do 2 augmentations. Take any other image from a data set and do the augmentation. And more often than not, they will not be the same class. So in general, in expectation, this idea holds that even without knowing labels, I can make these self-label type approaches where I say these are the same. It's very, very powerful. And this idea of using this as a pre-training step, like a learning representation step, before basically training a classifier is common in state-of-the-art image classification models at the moment. Pre-training step on a very, very large unlabeled data set. Now, this is contrasting using an idea of augmentation, saying that I've got cases where 2 things should be the same, and I've got cases where things should be different. But where the contrastive learning gets really interesting around representations is when you use much more novel ideas about what is similar and what isn't similar. My favorite example came from robotics. This is the first example I saw of this idea of contrastive learning. Say, for example, I have a robot arm that is reaching into a tray and it's picking objects up. And I want to learn some sort of network, or some sort of, you know, pre-train a network that is sort of understands something about the pose of this arm. And by the pose of the arm, I mean sort of the description in joint space of where this arm is. So, if, you know, for example, our arms, we can think about a rotation and a bend. And, you know, my arm is located in space according to some series of numbers. So I want to learn an encoding of the arm. What I can do, which is, I think, is a fascinating idea. So I'm going to actually take a scene with a robot arm, sort of, in this case, simulated, reaching into a tray and coming back up. And I'm going to actually have 2 cameras viewing this robot arm. And the reason I do that is because I have an idea about time. Things being at the same point in time should be the same, whereas things under the idea that the arm is always moving, 2 things that are different in time should be different. So if I'm interested in using a data set like this to learn a network, pre-training a network that's good to sort of learn a representation around the arm pose, I can do the following. I can take these 2 cameras that are sort of recording at the same time, and I can take 2 of the images from different cameras at the same time. Now, and there's an invariant that holds here that I know, even though in pixel space these look very different, the arm is in the same position because the camera images were taken at the same time. So I can use these 2 images as examples that go to the network to say, I don't care where you put the encoding, I just need these 2 to be next to each other. And you can see this is actually potentially quite difficult because in pixel space, these look fundamentally different. It's like the augmentation we're talking about, where we're making a change that's invariant to the class, but it's a lot more difficult here because the pixels are quite different. And in the same way we had the example before of things that are the same, under the assumption the arms are always moving, we can also say that if the arm is moving, then 2 images from the same camera at different times should have a different arm pose. And I want the encodings for these to be different. Now you can really see here, this is difficult because it's only the arm that is moving in this case. So for these two to have different encodings, the network really needs to focus on the thing that's changing, which is the arm, even though in general pixel space, these are quite similar. This example of contrasting over time comes from a paper called Time Contrastive Networks by an ex-colleague, Pierre. And this is the one that really got me into contrastive learning that I thought was such a great result, because we've got an effectively endless amount of data here. All we need to do is move this arm around, have two cameras that we know are taken at the same time, and use that contrastive invariance to say two images at the same time should have the same encoding. Two images at different times need different encodings. And because more often than not that is generally holds true, we can use that as a learning objective to pre-train a very, very large network. That's fascinating. Now, there's so many cases where you might want to use this. This may work on other cases in vision, for example. This is a quick image I took from a screenshot from an NVIDIA Drive Labs video, and it shows these object tracking they're doing, and I didn't really pick it because of that. I just picked it because this is a good example of the different frames and videos you might have on a self-driving car. So that idea of contrastive learning could hold here as well, because we know the time is the same. So for example, any two pairs of these videos should in some way, if we were pre-training, act as things that represent the world as a whole at the same time and should be the same. And you can think about the ones on the top row here, the forward-facing cameras. Any two pairs of those should be a similar enough encoding that we could use this as a pre-training step for a network, which is very, very, very powerful concept indeed. But really the contrastive learning idea is that what can you imagine? What can you put around your data to say that there are two things that are the same? For example, two microphones in the same room that are recording audio, even though they'll fundamentally have different signals, because again, it's at the same time, you should expect things to be the same. And so an encoding should be the same. It's a fundamentally really super powerful idea. So that was fundamentally it, my idea of talking about reusing representations that have come from pre-training, particularly in contrastive learning, and how this is basically one of the next waves of what we see for transfer learning. So thanks so much for listening.
This module, we covered some advanced computer vision concepts for you to consider. We spent most of the time talking about object detection, which is an important concept in embedded vision. In most cases of object detection, we are trying to uniquely identify each instance of an object type in an image and then figure out its location. We do that by generating what's known as a bounding box that consists of x, y coordinates of the object and the width and height of that object in pixels. Note that some bounding boxes give you center coordinates and some give you the top left of the box. Either way, you can use that information to figure out where the approximate center of the object is for your project. This can be very useful for something like having a camera automatically track a person or animal, or having a self-driving vehicle automatically avoid pedestrians and other cars. One obvious way to accomplish object detection is to slide a window over the whole image and perform inference on whatever sub-image is under that window. If the object is found, you can highlight wherever that window was to create a series of bounding boxes. However, this has a number of problems. A single object might generate more than one hit. Without additional steps, the system might see my dog as 3 different dog objects. Also, it will generally only find objects that fit completely inside the window. If an object is too large or too small in the frame, it will be missed. You could slide windows of different sizes over the image to look for large, small, near, and far objects. However, this illustrates the third problem with this approach. It's very computationally expensive. You have to perform inference on every single window, which could take a long time. This might be okay if you only need to look for objects in a still image once every minute or so, but you likely won't get a usable frame rate on live video streams. That's where we introduced this concept of region proposal. Modern object detection algorithms focus on only a few areas of the input image that might contain objects. Image classification is performed on these regions, which cuts down on the number of times inference needs to be performed. That gives us a more complex model that can be trained and used to perform object detection. We feed the model our input image and it outputs a list of objects that it detected. Each object contains the predicted class, a probability or confidence score of that class, and a bounding box coordinates and size. We can use that information to draw the bounding box on top of our image to give us an idea of what the model found. To train such a model, we need to provide the training process with ground truth bounding boxes and labels for each object of interest in a set of training and test images. From here, information about the regions can be combined, or the window with the highest confidence can be selected to determine where the objects appear in the image. From there, we looked at how we can evaluate object detection models. To begin, we would graph the recall versus precision for each label as we moved the classification threshold from 0 to 1. At each threshold value, we can calculate a precision and recall score from the validation or test set. We then estimate the area under the precision recall curve by averaging 11 different points. To determine if a bounding box is considered good enough, we would compare it to the ground truth bounding box and calculate the intersection over union. This is where we first find the area of overlap between the two boxes and then divide that value by the area encompassed by both boxes. If this IOU value is above some threshold, normally 0.5, we would say that the bounding box is a true positive for that particular object. This is, of course, assuming that the predicted bounding box and ground truth box are of the same class. The mean average precision is a common metric used for measuring the performance of an object detection model. One way to compute the MAP score is to calculate the average precision for each class at a given IOU threshold, like 0.5, and then find the mean of those scores. Some newer papers and competitions rely on finding the mean of the average precision scores for all classes across a range of IOU thresholds. This helps to give higher scores to models that are more precise with their bounding box placement. We then looked at a number of popular object detection models. The first was a region-based convolutional neural network. Here, a region proposal algorithm identified areas of interest that were sent to a convolutional neural network and classifier. This information was also sent to a regression model that updated the location and shape of the regions to create better bounding boxes. Next, we examined fast RCNN that built upon the ideas from RCNN. Here, the region proposal happens in parallel with the convolutional stages of the model so that feature extraction only needed to be performed once, thus saving some time during training and inference. Faster RCNN takes this a step further and performs region proposal on the feature map instead of the raw input image. To do this, the authors use a neural network for region proposal instead of some other algorithm like selective search. They called this approach a region proposal network. Finally, we looked at the single-shot multi-box detector that performs feature extraction, region proposal, and determines object location in one pass through the network instead of needing to do classification on each region of interest. By performing classification and bounding box regression on the output feature map of each convolution stage, the image is essentially divided up into a series of different sized grids, where each cell has a variety of potential default bounding boxes. The classification heads determine if the proposed bounding boxes belong to one of the classes or the background. Redundant overlapping bounding boxes are removed in the non-maximum suppression stage so that we end up with, ideally, one box per object. The output should give us unique bounding box and classification information for each object in the input image. Note that at this time, the SSD model we use in the course only works with color images, so we can't save on processing time by converting everything to grayscale. I showed you how to use transfer learning in Edge Impulse to train your own object detection model and then deploy it to a Raspberry Pi. Finally, we touched on some advanced concepts that, while outside the scope of the course for now, are important to keep in mind if you are working on an embedded computer vision project. These are just a taste of what's actively being researched in computer vision. I briefly talked about the idea of image segmentation and how it can be used to discern object shape. I also went over a few papers that showcased some popular image segmentation models. We also heard from Dmitry Maslov, who gave us a multi-stage machine learning demonstration. This helps us see how we can use multiple machine learning models in tandem to meet our needs rather than trying to come up with a single model for our project. Finally, we got to hear from Matt Kelsey, who showed us how we can reuse representations or encodings from the middle of a machine learning model. We can use these representations to create a self-supervised learning system. Object detection is exciting, and we're just now starting to see it work on embedded systems thanks to a bunch of research that went into optimizing both hardware and software.